Hi, my name is Gonçalo Castro and I'm going to tell you about my master's thesis titled Gravitational Waves and Massive Gravitons, which will be written under the supervision of Professor Vítor Cardoso of Centra in IST. You've probably heard at least some of the words in the title, but to properly understand what they're all doing there, we should start from the beginning. In 1915, Albert Einstein first proposed his theory of general relativity. According to it, we can think of space and time to be a single four-dimensional entity, deformed by massive bodies, such as stars and planets. These deformations then rule the trajectories of other bodies, such as our planet's orbit, us falling from a staircase, and even the path of a ray of light. The predictions of this theory are tremendously accurate, and its validity has been confirmed in many different regimes. More recently, we have even directly confirmed the existence of gravitational waves, oscillations of space-time itself. However, all is not well, otherwise I wouldn't be filming this video. The subject of my thesis is motivated by two problems, an observational one and a conceptual one. The first is the rate of expansion of the universe. We can model the universe through the theory of GR and, based on what we know, we would get to the conclusion that the universe should be expanding but at an ever slower rate, due to the gravitational attraction of its galaxies. However, experiments tell us that the opposite is happening. Actually, the expansion of the universe is accelerating. So, either there is something else in the universe we don't know of, and this is the idea behind dark energy, or gravity does not behave exactly as we expect. The other problem is that the theory of GR is completely classical, meaning that it does not take into account the ideas behind quantum mechanics, as one would expect it should, given they have also been shown to be valid. An attempt to join these two concepts would certainly give us a more general theory, of which GR would merely be an approximation, although a good one. Following this through, we could build a quantum theory of gravitation, as has been done for electromagnetism. In this case, it was posited that electromagnetic waves, also known as light, could also be described as particles, called photons. By its turn, this photon could be used to describe the electromagnetic force that two charges feel. In the same way, we could propose a particle, called a graviton, that describes how bodies with energy interact, and that has an associated wave phenomena, gravitational waves. This graviton would then describe how massive matter, like stars, or matter with energy, like light, interact. This description would actually give us something very similar to GR, not solving the observational problem we had. However, we can make a simple change to the theory to make it work. Considering a graviton that is not massless like the photon, but has a very small mass, the behavior of gravity at long distances is changed, possibly solving the expansion problem. But we would also like to have some other way of testing whether this massive graviton idea is right or wrong. Fortunately, it is expected that its mass slightly changes the signal of gravitational waves, such as the ones that have already been detected by the Virgo and LIGO detectors. And, finally, it is here my dissertation comes into play. My work will be to calculate what is emitted, in terms of gravitational waves, when a body falls into a static and stationary black hole, the simplest kind there could be. Not for the theory of general relativity, but for a theory of massive gravity. While the waves emitted by these occurrences probably cannot be measured by our current detectors, it is highly likely that future detectors, such as the LISA, will be sensitive enough. Then, we will be able to test whether the graviton can indeed be massive and probe deeper into the nature of gravity.